In part 1, we obtained the basic power voltage curves from the PV cell model and described the maximum power point. In part 2 here, we will discuss the effects of the series and shunt resistances of the PV cell on the power voltage characteristics and also on the maximum power. We will also study the effect of this diode non-ideality indicated by the ideality factor A also on the PV power voltage characteristics. This is a family of power voltage curves for a single PV cell under different solar irradiance levels. The power is 0 at both the short circuit current points here as well as at the open circuit voltage points here. And the power reaches a maximum value at a point called the maximum power point. So the power at this point is the PMP, or the maximum power. The maximum power changes proportionately with the solar irradiance level, and for example, the maximum power point at 1000 watts per meter squared is here. The maximum power at 800 watts per meter squared is this power, and so on. Now we also saw that in the previous videos that the temperature also has a significant effect on the power voltage curves, and it brings down the maximum power value with rise in temperature. Next, we will look at the effect of different parameters of the PV model on the power voltage curves, starting with this series resistance RS. I will show an animation created in MathCAD illustrating the effect of continuous variation in this series resistance on the power voltage curves. Now, the reference plot that you see here corresponds to the ideal case, meaning the series resistance RS or RS1 as shown here is 0 for this case. And this is the power voltage curve, and this blue is the current voltage curve, IV characteristics. And the operating condition corresponds to an irradiance of 1000 watts per square meter, and the corresponding maximum power with zero resistance is shown here. It's 4.16 watts, and the fill factor also for this zero resistance case is rather high, it's 0.8. Now when I run the animation, notice how the power voltage curve changes as I increase the series resistance from 0 to roughly about 40 milliohms, which is about 10 times the nominal value of a typical commercial PV cell. Okay. So the dotted lines are the IV and the PV curves corresponding to RS equals 0, and the solid blue and the green curves are the IV and the PV curves respectively for the varying series resistance. The value of the RS also is given in this box, and the corresponding maximum power for each value of RS is given here, and the fill factor is shown at this point. Okay, so we can clearly see that the effect of the series resistance is much more pronounced at the higher voltage points around the maximum power point and after that. So that is where we see both the IV curves and the PV curves. They have essentially the slope is very different, especially near the open circuit voltage. The absolute value of the slope of both of these curves, they actually decrease with increasing series resistance. Okay, so let me run this manually to see the effect of RS more clearly. So, okay, this is the case when RS equals 0, and if I increase the value of RS to, let's say, about 4 to 5, let's say 4.5 milliohms. So that is the typical value for the series resistance of the type of PV cells that we've been considering here and in the previous videos. So corresponding to this typical value of RS, the maximum power is 3.9 watts for this single cell, and the fill factor is 0.75. So if you recall, this is the value that we had when we introduced the definition of the fill factor for the first time in part 1 of the video. So if I increase the series resistance to, let's say, twice this value, say about 9 or 9 milliohms, we can see now the slope has the absolute value has become smaller, the slope, and the maximum power is also lower than the previous case, and the fill factor has come down from 0.75 to about 0.7. Okay. And if we increase the series resistance further, notice the slope decreasing, the absolute value decreasing, and around this maximum value, which is roughly 10 times or slightly less than 10 times that of the typical value of 4.5 milliohms. You can see the maximum power is drastically reduced. It's about 2.1 watts, and the fill factor is also significantly lower at 0.4. Also note that the maximum point voltage, the VMP, that is the voltage at which the maximum power occurs, has also very significantly changed with the series resistance. So for this RS equals 0.03, the maximum power occurs somewhere around 0.34, whereas at zero resistance, it was somewhere around 0.55 or 0.52. Okay, so in fact, we use this slope of the IV curves mostly at the open circuit voltage point to make an estimate of the series resistance if we have the measured IV or the PV plots available. Okay, so next we study the effect of the other resistance, the parallel or the shunt resistance, on the power voltage curves. So once again I show the animation where I change the shunt resistance continuously. So this time I change it from about 10 ohms, this is for a single PV cell, to about about 0.2 ohms, which is not a realistic value. Like 0.2 ohms may imply either a failed device or problems in the manufacturing process. Okay, so the value of the actual shunt resistance in the animation is shown here as well as in this bar chart, and the maximum power corresponding to each of those shunt resistance values is shown in this box as well as in this bar chart. Okay. And the fill factor again for each of the shunt resistance values is shown here. Okay. So let me run the animation. So you can begin to see that the main effect on both the IV curves as well as the PV curves is at the lower voltage end. The IV curves, they begin to drop at a faster rate, and the PV curve, this green, it increases at a reduced rate for low values of the shunt resistance. Remember that we are actually reducing the shunt resistance from 10 ohms to a very low value of 0.2 ohms. So in response, the PV curve, the rise in the power is slower at the lower voltage end. So the corresponding values of the maximum power are shown here, and you can see with 10 ohms it was close to 4 watts, and it is come down to about let's say it's about 2.5 watts at 0.2 ohms, yielding a very low fill factor of less than 0.5. So the main point is that lower the value of shunt resistance, lower is the maximum power, and lower is the energy captured for a given irradiance level. And one effective way to determine the shunt resistance from the IV plots is to look at the slope of the current versus voltage curve near the short circuit current region. So the last slide is on the effect of this diode non-ideality quantified by the ideality factor A on the power voltage curves. So the ideality factor A is a measure of the material quality, with lower values reflecting better material because of the smaller reverse saturation current IO, and therefore resulting in higher maximum power. And typical values of A is between 1 and 2. The plot here shows the power voltage curves along with the current voltage curves for 3 different values of the ideality factor A. For A equals 1, 1.2 and 1.5, with the pink curve corresponding to A equals 1, the blue is A is 1.2, and the brown is 1.5. Okay, so clearly the effect of the ideality factor A is more pronounced near this maximum power point. For better material quality, A is smaller, and as seen from these three plots, smaller value of A corresponds to higher maximum power. The pink PV curve has the highest MPP value. So by matching the model, the PV curves obtained from our this equation or from our PV cell model, comparing that with the measured PV curves near the maximum power point, we can extract the value of this ideality factor A. Just as the slope near the open circuit voltage is used to estimate the series resistance, and the slope of the IV curve near the short circuit current gives us the value of the shunt resistance. Similarly, we can use the curves at the maximum power point to estimate the value of factor A.